Hey everybody, Trey here. Welcome back to another episode of this Skew-T and Hodograph series. In our last few videos, we've begun to discuss every single parameter, every single box of these SPC and model soundings. We have gone through the Skew-T here on the top left, the Hodograph here on the top right, and in our last video, we started to discuss every single parameter here on this bottom half of the sounding. We started over here with this bottom left box. We went through all the different parcels that are listed here, and there are different variables, as well as some thermodynamic parameters that are listed down here in this kind of middle section. And we left off right in here. So now we're going to talk about these two parameters right here. We've talked about both of these in a previous video. WBZ is your wet bulb zero level, and the FZL is your freezing level. They are both related. And the wet bulb zero level, it kind of shows the same thing as the freezing level. The wet bulb zero level is basically the height at which the wet bulb temperature is 0 degrees Celsius. So we follow that 0 degree Celsius isotherm up to where it intersects with the wet bulb temperature profile. Again, that wet bulb temperature profile is that wet bulb, it takes into account evaporation, etc. We talked about that in a previous video. But where that 0 degree isotherm intersects this blue profile here, that wet bulb temperature profile, is that wet bulb zero level. In this case, it's about 10,176 feet. It's measured in feet. And the freezing level is where the 0 degree Celsius isotherm intersects the actual environmental temperature profile. So we follow that 0 degree Celsius isotherm up to where it intersects the environmental temperature profile, and that is your freezing level. Also in feet. In this case, it is about 12,366 feet above ground level. So these aren't super important. I don't use them too often. They are good parameters to use when forecasting for hail. The higher these are, the less likely you are to see large hail reach the surface. The lower these are, the more cold air aloft you have, the more likely it is for hail to reach the surface. But again, you can tell a hail kind of setup from looking at the overall profile, but these are decent in telling you how much cold air aloft you have and the likelihood for large hail to reach the surface. All right, so now we'll talk about the convective temperature, or ConvT. We've talked about this as well in a previous video. ConvT is your convective temperature. It's that lowest temperature that air must be heated to in order to become buoyant. So it's basically that the air temperature that needs to happen at the surface, that needs to be reached at the surface in order for parcels to be able to rise on their own. This is a decent parameter to use. I've used it in forecast discussions videos before. I do look at it sometimes. It is more applicable in setups where you only have sort of surface heating as the main lifting mechanism, because you can have, in a typical severe weather setup in the plains per se, you can have the lift from a large-scale trough that can lift a capping inversion and cool the atmosphere and help convection go up despite maybe a very high convective temperature. So it's more applicable for setups, your more air mass thunderstorm setups, but it is a decent parameter to use. I do use it when I'm making severe weather forecasts, because if you have a convective temperature, in a normal sort of setup that is 110 degrees Fahrenheit, then you're probably looking at a very strong cap at the surface, one that may not be able to be breached without some very strong outside influences. So convective temperature I do use sometimes, but again, it is a little bit more applicable for your more air mass thunderstorm setups than it is for a typical severe weather setup with a large-scale forcing mechanism. Then finally here we have our MaxT, or max temperature. And the maximum temperature, we've also talked about this before, that is going to be your estimated maximum afternoon high temperature, basically. It's as we've discussed before, you bring down the parcel at 100 millibars above ground level, you bring it down along the dry adiabat, and then you add 2 degrees Celsius for that super adiabatic contact layer. Fancy speak for you're just adding 2 degrees to whatever happens when you allow the parcel to descend from 100 millibars above ground level. It's basically an estimate of afternoon maximum temperature, not applicable really for severe weather forecasting. I've really never used it at all, but it is a decent estimate for afternoon high temperature. Of course, it is just an estimate. There are lots of factors that can modulate the actual high temperature that does occur in a given location, but you can estimate it from the sounding. Not very useful in severe weather forecasting. So now we'll talk about these last few here in this middle section on the right-hand side here. These are all going to be, for the most part, these first three are going to be composite parameters that I really don't use that often. I really don't like to use composite parameters because they're just kind of a snapshot. They take into account just a couple of ingredients amidst an entire pantry of ingredients that you need for a potent severe weather event. So I don't like to use these, and I really have never used any of these first three parameters here when making a forecast. But we'll go through them here each. This first one on the top is WNDG. That is your wind damage parameter. And it basically tells you how well large instability, large CAPE, steep low-level lapse rates, enhanced flow in the mid-levels, and low convective inhibition are co-located. And we can calculate wind damage, the wind damage parameter, as follows. So we take the mixed layer CAPE, divide it by 2,000 joules per kilogram. We multiply that by the quotient of the 0 to 3 kilometer lapse rate, divided by 9 degrees Celsius per kilometer, multiplied by the mean wind in the 1,000 to 3,500 meter layer above ground level, I will mention, divided by 15 meters per second. So again, you can see we're standardizing kind of all of these values here. Finally, times the sum of 50 plus mixed layer sin divided by 40 joules per kilogram. So a very complicated formula, and one really that doesn't matter in the grand scheme of things. You can tell the potential for strong damaging outflow winds by looking at the sounding, looking at the distribution of the lapse rates, the moisture content in the upper levels of the atmosphere. This really is just mumbo jumbo. Really not a great way of assessing the wind damage potential in a certain environment, but it does take into account, where, how co-located strong instability, steep low-level lapse rates, enhanced flow in the mid-levels, and low convective inhibition, how well they're co-located, as these are all kind of helpful in their own right in diagnosing the potential for wind damage in a given environment. So then we have the ESP right here, and ESP is enhanced stretching potential. I'll abbreviate potential as POT. Enhanced stretching potential. And the enhanced stretching potential takes into account where low-level buoyancy and steep low-level lapse rates are co-located. And it takes into account our 3 CAPE parameter that we talked about a little bit ago. And generally, the theory goes that if you have higher enhanced stretching potential, then you may have higher chances for tornado genesis. And ESP is calculated as follows. You take the 3 CAPE divided by 50 joules per kilogram. So we're standardizing these. And then we multiply that by the 0 to 3 kilometer lapse rate minus 7 divided by 1 degree Celsius per kilometer. So we're trying to get rid of the units here so we can get a kind of a unitless parameter in enhanced stretching potential. Basically tells us how strong, the ability for this environment to stretch any spin or vorticity near the surface into the vertical. Again, the higher the enhanced stretching potential, the higher the low-level buoyancy, the higher the low-level lapse rates are, the steeper the low-level lapse rates are. And if you have that with, again, co-located with, a high amount of spin or vorticity in the low levels, then you may have an enhanced chance for tornado genesis in any supercell in this environment. Again, I like to rely on that 3 CAPE and surface vorticity combo, more than this enhanced stretching potential combo. And this becomes more of a factor in sort of landspout, tornado type, non-mesocyclone tornado type setups. But again, I like to favor that 0 to 3 kilometer CAPE and surface low-level vorticity combo when diagnosing the enhanced potential for tornadogenesis in any supercell in a given environment. And then we have our MMP right here. MMP is our MCS maintenance probability. And basically just tells us how likely it is that a mature MCS will be able to maintain itself within an hour of a given sounding. So this is, again, as the name suggests, it is much more, viable for when you're forecasting for mesoscale convective systems, but it is not really applicable for, your tornadic supercell type events. And the way we calculate MCS maintenance probabilities, we take into account these three factors. I don't have an equation for you here, but we take into account these four factors: the maximum bulk shear in the 0 to 1 and 6 to 10 kilometer layers. So we have two separate layers here that we look at the bulk shear within. It's that 0 to 1 kilometer layer above ground level and that 6 to 10 kilometer layer aloft. We take a look at the 3 to 8 kilometer lapse rate, the MU CAPE, most unstable CAPE, and the mean wind in the 3 to 12 kilometer layer. Mean wind. So these four, factors go into the MCS maintenance probability. Again, it's not useful for severe weather forecasting. I've never used it once in severe weather forecasting, but it is there if you want to see maybe the potential for an MCS to maintain itself in a given environment. And then this last one in this middle section on the SPC soundings. We'll take a look at the middle section here in a second, because there is a different parameter that is given on the model soundings. But this one on the SPC soundings is NCAPE, and this is short for Normalized CAPE. And we basically take the CAPE and we divide it or normalize it by the depth of the buoyancy layer. So we basically see, how high in the atmosphere does the buoyant layer extend, and we take our CAPE. You can use any one of these parcels, and we divide it by that depth of the buoyancy layer, which I'll abbreviate as D here. So this basically gives us a value that addresses the organization or construction of the CAPE within the atmosphere. Lower NCAPE values tend to mean a more tall and skinny CAPE profile, whereas higher NCAPE values tend to mean a more fat CAPE profile. So we've talked about this before. When you have a tall, skinny CAPE profile, your updrafts are not super robust. You do have a lot of CAPE, but it may be tall and skinny. It may be very, in a skinny sort of layer up in the atmosphere. Your difference between the parcel temperature and the environmental temperature is not that great throughout the environment. Even though you may have a high CAPE number, it may not be organized in a fat fashion. If you have more fat CAPE, or higher values of NCAPE, then you have more robust updrafts and parcel accelerations, upward parcel accelerations that are very fast in comparison to a tall, skinny CAPE profile. So NCAPE is generally going to be a very, very small value. NCAPE values near or less than 0.1 tend to suggest tall, skinny CAPE profiles, while NCAPE values closer to, say, 0.3 or 0.4 mean a more fat CAPE profile. So again, you can take a look at the CAPE profile by actually looking at the Skew-T itself, the parcel trace, and the environmental temperature itself. But this does give us a value, and I don't use it personally in severe weather forecasting, but I know a lot of people who do, and it is a decent way to tell us how the instability is kind of constructed in the entirety of that atmospheric profile. All right, before we take a look at the bottom portion of this left-hand box here, I want to take a look at the model soundings first for this middle section, kind of compare them to the SPC soundings. Now you're going to see all the same parameters for the most part as you see on the SPC soundings: precipitable water, mean mixing ratio, low level and mid level relative humidity, DCAPE, etc., etc. They're just organized and listed in a different order than they are on the SPC sounding. Now the difference here on the model sounding is, number one, you have a few that are omitted on the model sounding. Wet bulb, zero height, freezing level, etc. But you also have a few parameters that are on the model sounding that are not on the SPC sounding. The first of which is going to be this TT value right here. And that, as we've discussed before, is our total totals index. And we discussed this in a previous video. It's another one of those composite indices that helps us, gives us a quick snapshot of whether or not we're likely to see deep convection or thunderstorms in a given environment. And just as a refresher, the way we calculate total totals is we add up the vertical totals and the cross totals. The vertical totals are the difference between the 850 and 500 millibar temperatures. We then add that to the cross totals, which is the difference between the 850 millibar dew point and the 500 millibar temperature. So that is our formula for the total totals index. Anything in the 40s, usually above 45 or so, is favorable, is an environment favorable for thunderstorms. But again, we're neglecting things like wind shear, and so total totals doesn't give us the ability to see how severe these thunderstorms might be, etc. So don't really use it. Just like the K index, it's kind of really useless, but it does give us a brief snapshot, kind of one value that shows us how unstable the atmosphere might be. The next one here is this TEI value right here. And TEI stands for Theta-e index. And what the Theta-e index tells us is it gives us a diagnostic variable for the chances for elevated convection. So it's not super important in the grand scheme of things when making a severe weather forecast. Never used it one time in making a forecast. But it is one of those composite parameters, and the way we calculate it, this value displays the difference between the Theta-e at the surface and the minimum Theta-e in the lowest 400 millibars of the sounding. So you take the difference of those two, and that's your Theta-e index. Again, it tells us the chances for elevated convection. The higher the chances are, the higher the Theta-e index is, the higher the chances for elevated convection. So in this particular sounding, it's 23. That's pretty high. Usually values above, say, 9 or so there's a very high chance for elevated convection. But again, it's a pretty useless parameter, not something that really is important when you're making a severe weather forecast. Then there's this final one here, this MBURST right here. I haven't been able to find a lot of documentation on it. I've never used it before, but just given the name, I believe it's some sort of microburst potential sort of parameter here. Not 100% sure again what it means, but it is there. It is going to be on your model soundings and not your SPC soundings. But I would assume it's a microburst parameter, not important in the grand scheme of things when making a severe weather forecast. So we'll now finish things out with this bottom portion of this left-hand box here on the bottom. We'll start off at the very bottom left corner of the Skew-T, and these are going to be your lapse rates for different layers of the atmosphere. We have a few different layers that are given here. This first one is the 0 to 3 kilometer above ground level layer. Then we have the 3 to 6 kilometer lapse rate. And then we have between the mandatory pressure levels, we have the 850 to 500 millibar lapse rate and the 700 to 500 millibar lapse rate. And as we know, lapse rate is the rate of change of temperature with height in a certain layer. And I do look at these when I'm making a forecast. It tells me kind of how strong updrafts might be, how robust they might be in a given environment. I also look at them for the potential for maybe some large hail. Steep lapse rates do sometimes translate to large hail with some other diagnostic parameters. But if I see lapse rates, up above 7, inching toward 8 and 9, I know that the updrafts are going to be pretty strong, pretty robust. Updraft partial accelerations are going to be pretty fast. That means updrafts will be robust and the potential for large hail is likely there. Now, if lapse rates are like here, we see, towards 6, lower than 6. I know that those lapse rates, pretty weak parcel accelerations there, and in certain layers may feature parcel accelerations that are more weak, less updraft strength in certain layers. So it just kind of helps me see the construction of the possible updraft strength in a given environment. Also helps to assess, among other things, the large hail potential. And then finally, we'll move to these composite parameters here, these color-coded parameters here. These are our significant tornado and supercell composite parameters. So SCP, supercell composite, and STP are significant tornado parameters. Once again, these are composite parameters, so they only take into account a few different variables. And so they're not extremely reliable when making a forecast. But these top two here, the supercell and left supercell, these are going to be our supercell composite parameters. And they take into account CAPE and shear. And the way we calculate the SCP here, at least on the SPC soundings, is we take the most unstable CAPE, we divide that by 1,000 joules per kilogram. We then multiply that by the effective SRH, which is listed down in here, effective inflow layer SRH. We divide that by 50 meters squared per second squared. And then we multiply this by a final term that takes into account the effective bulk wind difference, or basically effective bulk shear, listed down here, divided by 10 meters per second. So once again, we're kind of standardizing all of these values to get kind of one sort of unitless value that helps us assess the potential for just supercells, rotating thunderstorms here. You can see we're using most unstable CAPE. We're not using mixed layer CAPE. So most unstable CAPE often involves elevated storms. So this doesn't tell us if storms are going to be surface-based or elevated. It only tells us if storms have a higher chance of rotating. In other words, becoming supercells in a given environment. So supercell composite parameters, generally supercell composite parameter greater than 1 means an environment that is favorable for supercells. You can see in this environment, we're seeing an SCP of 16.3. That is extremely, extremely high. So the threat for supercells in this environment is very, very high. Anything less than 1 tends to means an environment that is less likely to produce supercells. And so I always like to look for values that are greater than 1, but again, I don't really use this parameter all that much because it is a composite parameter. It only takes into account a couple of things. It doesn't take into account moisture, etc. So not really something I look at. Now, left supercell is going to be our left-moving supercell parameter. And this would take into account sort of negative SRH. You can see in this kind of environment, we see large clockwise curvature in the low levels, clockwise curving hodographs. So in this case, a right-moving supercell would be favored. But if we had negative SRH, we had a hodograph that looked maybe something like this, we would see more of a left-moving supercell that's favored. You can see in this case less than 1 here, so a left-moving supercell not going to be favored nearly as much as right-moving supercells would be in this environment. Then we have these two. Those are going to be your significant tornado parameters, or STP. Your significant tornado parameter tells us basically the chances for a right-moving supercell to produce EF2 plus tornadoes. And the way that significant tornado parameter is calculated is going to be, it's a pretty long formula here, but it takes into account the mixed layer CAPE divided by 1,500 joules per kilogram times the effective SRH divided by 150 meters squared per second squared times the effective bulk wind difference divided by 12 meters per second times 2,000 minus the mixed layer LCL divided by 1,000, and then finally times the mixed layer SIN plus 200 divided by 1 50. So you can see it's a big old formula, basically takes into account instability, wind shear, storm relative helicity, how high the cloud bases will be in the LCL, how much convective inhibition there is. Because all of these are important on a holistic sense in telling us whether or not we're going to see significant tornadoes, or whether we have a chance of seeing significant tornadoes. And of course, the higher this is, the higher the chances for a EF2 plus tornadoes with any right-moving supercells in a given environment. Now, this is going to be your effective layer STP. We can use a fixed layer STP, and the fixed layer STP takes into account instead of using the effective bulk wind difference and the effective SRH, we would use the effective SRH, we would use the 0 to 1 kilometer SRH. So a fixed layer here instead of the effective SRH, which changes based on the effective inflow layer. Instead, we're using the 0 to 1 kilometer layer. That is going to be fixed. And then for the effective bulk wind difference, we're using the 0 to 6 kilometer layer. So we're not using the effective layer, we're using the fixed 0 to 6 kilometer layer for the effective bulk wind difference. So you can see how it would vary a little bit. The effective inflow layer SRH is different than the 0 to 1 kilometer SRH. The effective bulk wind difference is going to be a little bit different than your 0 to 6 kilometer shear usually. So you can see how some differences apply there. The effective layer one is a little bit more accurate because we do kind of look at the effective inflow layer SRH and the effective bulk wind difference and those kind of modulate supercells and tornadic supercells a little bit better than a fixed layer. But again, these are both composite parameters and ones that I'm never going to be using in a severe weather forecast, because we can find the threat for supercells and the threat for strong tornadoes based on a lot of other factors within this Skew-T and other products. And then finally here, this one at the bottom is your significant hail parameter. So your significant hail parameter, another composite parameter, it tells us, using a database of old events and observed proximity soundings from large hail events, it tells us the probability for significant hail, meaning hail that is greater than 2 inches in diameter. So the way we calculate the significant hail parameter is we take the most unstable CAPE. We're going to take the most unstable CAPE times the mixing ratio of the most unstable parcel times the 700 to 500 millibar lapse rate times the 500 millibar temperature in degrees Celsius times the 0 to 6 kilometer wind shear, our effective bulk wind difference in meters per second. We're going to take all of that and divide it by 44 million. And this gives us a significant hail parameter. Of course, again, the higher the significant hail parameter, the greater the threat for hail greater than 2 inches in diameter. But again, it's a composite parameter. It just takes a few things into account, not a holistic evaluation of the significant hail threat in a given environment. So I don't like to use this parameter as well, as it neglects too many things for it to be a useful parameter. So with that being said, that'll do it for this video. We've taken a look at every single parameter here in this bottom left box here of the sounding. In the next video, we are going to move on to this middle box here, and this is going to be our kinematics box. We took a look at the thermodynamic parameters today. We'll take a look at the kinematic parameters in the next video: storm relative helicity, bulk wind shear, etc. And then we'll close the series out by looking at these boxes here on the bottom right portion of the sounding. So with that, that'll do it for this video. Thanks for watching, and we will see you in the next video.